and that one being the quotient rule. Well, actually, now that I think of it, you're gonna do another one of these ones with f of x and g of x notation. But for now, we're gonna focus on our quotient rule. The quotient rule is what it sounds like. We're trying to find the derivative of a quotient of two functions of x. So let's go back to our definition of a derivative. We will have the limit as h approaches 0 of f of x plus h over g of x plus h. That's just because I substituted x plus h for the inputs right there. And then minus f of x of g of x. Again, just looking at those two. And then all over h. Now, this is already a little bit more complicated than we're used to, but we can split this into something a little bit easier to calculate. Instead of having this h on the denominator, which I think kind of throws us off a little bit, we can write this as a fraction, because anything divided by h, let's say y divided by h, is the same as y times 1 over h. If it helps to think of it, you can reimagine it as a fraction, like h over 1. And if you've done fraction division, you know you need to flip it and then change it back to multiplication. So we're going to factor out a 1 over h times f of x plus h over g of x plus h minus f of x and g of x. Now we're going to have to simplify this even further, so take a good look at this for a second. And I'll actually rewrite it once more so you don't have to take too much care for it. We're going to do the limit as h approaches 0. We'll take our 1h factored out, f of x plus h over g of x plus h, so minus f of x and g of x. Now, if you've done fraction subtraction, ooh, it's a rhyme. You can multiply, let me put the limit as h approaches 0 again. You can multiply these two, and then you multiply that one to that one, and then that one to that one, and keep the subtraction sign. I know I made that slightly more complicated than it needed to be, but I think you'll understand what I'm about to do. We'll have f of x plus h times g of x minus f of x times g of x plus h. Now, I actually want you to think about this for a second. Maybe pause the video. Well, not until I'm done with my little spiel. We're going to do what we did with our product rule, and we're going to add and subtract something on the numerator. I'd like you to actually think about this for a second and guess what we are going to add and subtract from our numerator. I'll give you a hint. We're trying to factor one thing out from our added and subtracted little composite function so that when we factor out something, it'll look like our definition of a derivative. Oops. So, I hope that you thought about that, but even if you didn't want to, I'll tell you right now, we're going to add and subtract f of x times g of x. So we have our limit as h approaches 0 times 1 over h, and then we will have f of x plus h times our g of x minus f of x g of x plus f of x g of x minus f of x g of x plus h. And then all of that, let me put a parentheses, is over, it's not over that, it's over g of x plus h times g of x, because we multiplied those two separate denominators when we were subtracting. Now, I hope you can see what we're going to do. We're going to factor out the 1 over g of x plus h and g of x. We're going to apply that same divided by h is equal to times 1 over h, or maybe not equal to, but the same as. And then we'll have the limit as h approaches 0 of 1 over, actually, you know what? I'm going to skip one step because I think you can handle it. We're going to factor out our 1 over g of x plus h times g of x. And then we're going to redistribute our h to this thing right there. That's essentially, you can kind of think of it as swapping. 1 over h is times, like, all of this, 1 over all of that, is the same as 1 over all of that times 1 over h. And if you've done, I'm not sure where this is taught. I think this is like some type of math course. You would know that would be called the commutative law of multiplication, which is a very complicated name for a very simple idea. But we're going to, arrange these in a way that I think might help you understand what we're going to do. We're going to have f of x plus h minus f of x. Oh, getting a tad bit ahead of myself. Times g of x minus f of x, g of x, minus our f of x times g of x plus h, plus our f of x, g of x. Now, if you were writing this out with me, just keep these to the right so that it's a little bit easier to understand what's happening. But, minus and plus, we can write this instead as minus parentheses minus, because that's what a plus is. So, minus a minus b is minus a plus b, and vice versa. So that's what we're going to do. We're going to, I hope you write that down if you are choosing to follow along. We are going to have the limit as h approaches 0 of 1 over g of x plus h times g of x multiplied by f of x. Well, I think you can follow along with me. If you remember, one second. If you can remember, we had our f of x plus h times g of x minus f of x times g of x. The only thing that we had in common between those was a g of x. So we can factor out that g of x from the numerator and then keep it out to the side, and we'll have f of x plus h minus f of x. And then I'm going to do this in one step. We're going to fragment our fraction. Since we had all of this stuff, everything on the numerator, all divided by h, we can break that into, a g of x, f of x plus h minus f of x all over h minus our f of x, g of x plus h minus g of x. Essentially, I split our function, since they have the same denominator, into two fractions with g of x and f of x factored out respectively. So, kinda already spoiled it, but in our second miniature function, we had f of x plus h times g of x. We had f of x times g of x plus h and f of x times g of x. The one thing that they have in common is f of x, and since it was minus parentheses minus, we will have to factor out a negative f of x times g of x plus h minus g of x, running a little bit out of space, but all over h, and I'll put parentheses. Now, if you've done limits before, which no shame if you aren't as experienced as you would like, I will do a limits video at some point. You can I suppose you can call it distribute. You can distribute the limit to multiple parts of the function if and only if those limits exist, which luckily for us they do. We're going to have 1 over the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of g of x times the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x over h. I'll put parentheses minus the limit, put another parentheses, as h approaches 0 of f of x times the limit as h approaches 0 of g. Wait. So, I kind of messed that up. With our function g of x, not with our function g of x, with this function right there, what we can do is we can let some random variable, let's say, I'm used to using u for substitutions, but, just to follow with his video, I'm going to use k equals g of x plus h minus g of x. And that's just some arbitrary substitution to make this a little bit more recognizable. So we're going to we're actually going to change our entire limit to fit with k notation instead of h notation. So as h approaches 0, k would approach what? Well, using direct substitution, we can do g of x plus h if h is 0, then g of x plus h is just going to be g of x minus g of x. Well, luckily for us, as h approaches 0, k approaches 0 as well. And, if we bring that g of x to the other side, we can say that g of x plus h is the same as g of x plus k. Oh, almost forgot the parentheses. That's the most important part. Now, I'm going to erase all of that. Hope you had at least a second to look at it. But with that newly found substitution, we're going to substitute the limit as h approaches 0 of f of, if you remember, g of x plus h is just going to be g of x plus k minus f of g of x all over, I'll write it out. G of x plus k minus g of x. G of x plus h is equal to g of x plus k, so that's where I substituted. And what's really nice about that is g of x and negative g of x, if you add them together, or I suppose if you subtract g of x from itself, you get simply 0, which makes that a much easier to look at function, and then times g prime x. So, with that, we can put it all together. I'm hoping that you see there is some similarity between the derivative, the limit definition of the derivative. Oh, whoops, totally forgot. I need to change our value that our function is trying to approach. It'll be k approaching 0. So if the definition of a derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h, then you can kind of see if k was synonymous with h, then that fits with itself, and if g of x was synonymous with x in that function, then that lines up. So we're going to apply our definition of a derivative using k instead of h. I mean, h instead in and of itself is already an arbitrary tiny distance. But yes, we're going to write that all of that, the derivative of f of, actually, let me write it down. I'll rewrite what we had beforehand. The limit as h approaches 0 of f of g of x plus k minus f of g of x all over k. If k and k and God, why do I keep putting h approaching 0? Maybe I'm just too used to it these days. But yes, it'll be synonymous with h for those ones. And then g of x will be our things for h. This whole thing is equal to the derivative f prime g of x. Now, I want you to pay close attention to the fact that the inside function, g of x, is not altered within this f prime. G of x is the exact same, but it is multiplied. Well, the entire thing is multiplied. I hope you got down most of those steps, because the derivative of f of g of x is equal to f prime g of x times g prime x. That's a very important rule. And another thing that you can take from it is, if you're trying to find, well, actually, you know what? I'm going to save that for a little bit later in this episode. But yes, pay close attention to that chain rule. And let me actually write down all the rules that we know so far. We have f of x plus or minus g of x. If we were attempting to find the derivative of that, that is equal to f prime x plus or minus g prime x. We also know that the derivative of c of f of x is equal to c times f prime x. We know that the derivative of a constant c is simply 0. And we know that the derivative of a product of two functions, f of x and g of x, is equal to, let me attempt to write some of this slightly more neat, because these are all very important and they deserve the correct amount of respect. G of x. The derivative of a product of those two functions would be f prime x g of x plus f of x g prime x. And then the quotient rule, or the derivative of a quotient of functions f of x and g of x, is equal to f prime x g of x minus f of x g prime x all over g of x squared. Okay. Oh, almost forgot the most important one so far. The derivative of f of g of x is equal to f prime g of x times g prime x. These are your best friends for the rest of your calculus career. Almost every derivative that you are going to have to do uses at least one of these rules, unless they're very, very simple. Most of the derivatives that you're going to have to do will use these rules, and perhaps in a later video I can work through some examples of how these rules work, but I really do just want you guys to understand as much as I can teach about like common derivatives. So I'm not sure if we'll have time for every common derivative that I want to show. I promise I will do some type of supplementary video where I go more in depth, either using worked examples or showing more complex proofs and or rules. But yes, those are all incredibly important. And not only will you need to memorize them, you'll also need to use them constantly. I don't think I have ever done any derivative that doesn't use at least one of those rules. So those are all very important. But what is also important is attempting to find the derivative of certain functions, like x to the n. We know that the derivative of x squared from that example oh so long ago is 2x, but that's not going to cut it. What is the derivative of like an x to the 8? You know, we can't do that over and over again, because if we were to use our definition of a derivative, we would have x plus h to the 8 minus x to the 8 all over h. I don't know about you, but without using Pascal's triangle, trying to do that full calculation will be annoying. So we're going to find a more general rule for the derivative of a function f of x is equal to f of x is equal to x to the n, and we are trying to find f prime x. Now, this proof is, I wouldn't say it's overly complicated, but it does use binomial theorem, which, no offense, I don't think many people are used to. Um, I can say personally that I hadn't seen binomial theorem in school for a very, very long time. And, like, while the binomial theorem does play a part in the math that you might do in high school and middle school, um, it's not really focused upon. So I'd actually rather use common sense to kind of prove why the derivative of x to the power of n is what it is. I mean, at the very least, I'll like show you what the binomial theorem is. You may or may not have seen it before, but if a plus b to the power of n is what we're trying to find, then this is equal to n choose 0, a to the n times b to the 0, plus n choose 1, a to the n minus 1, b 1, plus n choose 2, a to the n minus 2, b to the 2, and then plus on and on and on and on until you get to n choose n, a to the 0 times b to the n. Now, that's well, I should actually define what choose is. If you have n choose some random number r, that is equal to n factorial over r factorial times n minus r, parentheses, factorial. What was that? N minus r factorial. Now, that's a lot. I understand that. And it's also kind of not understandable if you haven't done a binomial theorem or even have seen the factorial, like within your general like math life. So I'm gonna try to use like common sense and a bit of Pascal's triangle. Now the Pascal's triangle, it's kind of like the binomial theorem. It just shows the coefficients of the terms in any binomial expansion, if that, not binomial expansion, but the word escapes me, putting the binomial to a specific power. So we're going to keep our a plus b to some power n, and then we'll have our Pascal's triangle goes 1, 1, 1, 1, 3, 3, 1. Whoops. Oh, I need more practice with my Pascal's triangle. It'll be 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. It's getting a little bit squished, but this essentially tells you what the coefficients of each of the terms in a binomial expansion of this form would be. So, if n was equal to 0, anything to the power of 0 is going to be 1. There's only one term in there. It'll be 1. So that's what the quote-unquote coefficient would be, even though it's just going to be 1 regardless. And then a plus b. What is up with my recording thing? A plus b to the power of 1. The coefficients of that would just be 1. It'll be a plus b. And for that, n equals 1. And then, you could do a plus b squared. We will apply that to that one. A squared plus 2ab plus b squared. the coefficient of a squared is 1, the coefficient of ab is 2, and the coefficient of b squared is 1 as well. And then, you can go on. I think you guys have at least seen a plus b cubed. That will be a cubed plus 3a squared b plus 3ab squared plus b cubed. The coefficient of a cubed is 1, the coefficient of a squared b is 3, the coefficient of ab squared is 3 as well, and the coefficient of b cubed is 1. And that just goes on and on and on. This is called Pascal's triangle. Now, using Pascal's triangle and a bit of common sense, we're going to try and find the derivative of our function x to the n. So we're going to we're going to go back to our limit definition of a derivative, and we will have the limit as h approaches 0 of f of x plus h minus f of x all over h. And that we know, since our f of x is equal to x to the n, we're going to plug that in, the limit as h approaches 0 of x plus h to the n minus x to the n. Now, for our binomial theorem, if you can remember what I had down, the first term in our expansion will be n choose 0 a to the n times b to the 0. That means that b to the 0 is 1. It doesn't matter. And then n choose 0 using our formula that we had along with our binomial theorem. N choose r is equal to n factorial over r factorial times n minus r factorial. So n choose 0 is equal to n factorial over 0 factorial times n minus 0 factorial. What does that mean? So factorial is a sequence. It is, let me erase that. It is n times n minus 1. I don't know what is up with this thing. It's equal to n minus 1, n minus 2, n minus 3, and on and on and on until you get to, let me put some ellipses, n minus n. You are essentially multiplying your number by every single number that is exactly 1 before it. So if you're trying to do the factorial of 3, that is 3 times what's, if n is 3, then 3 minus 1, or n minus 1 would be 2. And then 2 minus 1 would be, it would be 1. And then you go on and on. But 0 is not actually included in the factorial. Well, I can do a proof, not right now, but there is a proof to show that 0 factorial is 1. So I'm not going to, show you why 0 is not included in our factorial currently. But this is kind of like the limit, This is what our factorial is approaching. So 3 factorial is 3 times 2 times 1. So n factorial is n times n minus 1 times n minus 2 times n minus 3, and on and on and on. Oh, whoops, erased our exponent. We have n factorial, 0 factorial, and n minus 0 factorial. So let me put an equal sign because it's not multiplied. N factorial, we're going to leave the same. And then 0 factorial could show a proof, but right now I don't think we have the time. n factorial, 0 factorial is 1, and then n minus 0 is obviously n, so we're left with n factorial over n factorial. So that's 1. So essentially, the first term is always going to be a to the n for an expansion of a plus b to the n. So if we plug in x for a and h for b, the first term in this thing is always going to be x to the n. Right? There is no b, there's no h, term. I guess you can say it's times h to the 0, but there will always be x to the n. And as you know, there is another x to the n, one that is immediately subtracted out right there, so x to the n and x to the n. That first term is no longer going to be x to the n since we factor it out, or not, we're not factoring out, we're subtracting. We have x to the n minus x to the n, that is going to be 0, because x to the n is equal to x to the n. So our first term now is going to be, if we go back to our binomial theorem, it'll be n choose 1, a to the n minus 1, and b to the 1. Again, this might seem a little complicated, but we're going to break it down once more. We will have n factorial times 1 factorial times n minus 1 factorial. Oops, let me write both those slightly better. It'll be factorial, and that's n choose 1. Now, if we think back to our definition of a factorial, it is n factorial is equal to, n, it is equal to n times n minus 1 times n minus 2 times n minus 3, and on and on and on. And if we apply that same definition of a factorial to n minus 1 factorial, it's the exact same thing. It'll be n minus 1 times n minus 2 times n minus 3, and on and on and on. But n factorial has exactly one term more than n minus 1 factorial. If we remember that n factorial is n times n minus 1 times n minus 2 times n minus 3 times all that, then the only thing that n has more than n minus 1 is it has one extra n, exactly 1. So if we were to divide n factorial by n minus 1 factorial, what we're going to be left with is n, exactly 1n over 1, which 1 factorial, which would just be 1. So essentially, n choose 1 for this is just going to be n times a to the n minus 1 times b to the 1. Okay? Using our, if this is a plus b to the n, and we're trying to, plug in x for a and then h for b, this new term will be n times x to the n minus 1 b. Not b, it'll be h. Okay? And now, I could do this a couple more times just to show you, but I want you to pay real close attention. Using our common sense, well, not the common sense, we'll go back to our binomial theorem once more. The next term after this, the next term after that term is going to be n choose 2, a to the n minus 2 times b to the 2. I'm not even going to calculate and choose 2 because we have b to the 2 right here. And this is what I want you to pay attention to. If h is substituted for b, that means that this one is h squared. That means that there are two h's. H squared is equal to, h times h. So that means that if we were to divide by h, there will be an extra h for every single term after this term. This only has one h, and one h over one h is just going to be 1. Those h's cancel. But every single term after this term right here, every single term after this one will have another h. This one will be h squared over h, which means that there will be one h left. And then this next term, n choose 3 times, let me erase that. The term after that one would be, let me rewrite that, n times x to the n minus 1 h. The term after that one would be n choose 2, but we're going to go past. We're going to say n choose 3. That would be a n minus 3 b to the 3, or b cubed. That means that there is more than one h, and if b is h, then h cubed over h squared. And I could do on and on, but this is all to show you that there is only one term after we divide all of this by h. There's only one term that is left unaffected because the h here canceled out with that h right there. And that term is n times x to the n minus 1. Everything else, like they all have a single h, which means that if we were to directly substitute h, then those would just become 0. Like n choose 2, I'm actually going to leave it like n choose 2 right now. We would have x to the n minus 2 times h squared. This divided by h, it's going to be n choose 2 x to the n minus 2 h. That's what would be in this step, in this like weird scribble that I put down there. And if we were to directly substitute h for 0, regardless of whatever this comes out to, this whole like term right there, that's just going to be 0. And every subsequent term after this one, after that one, it's going to be 0. So all of this is to say that once we directly substitute 0 for that step, I'll rewrite it. Once we directly substitute 0 for n x n minus 1 plus, or yeah, well, okay, so it was x plus h, never mind, I'm good. We would have n choose 2, x to the n minus 2 h, and then on and on and on and on. All of this, once multiplied by 0 when there's an h, would equal 0. So everything past that one, that's all 0. Which means that the only thing that's unaffected when you substitute h for 0 is n to the x, n times x to the n minus 1. That means that the derivative of x to the n is n to the x times n minus 1. N times x to the n minus 1. And if we look at our Pascal's triangle once more, let me write that down. And on and on and on. That makes sense because if we go back to our x squared, we have, if we have x plus h, and we were to do a, expansion x squared, that would be x squared plus 2xh plus h squared, which means that the only one with exactly one h is 2. So, on our Pascal's triangle, the term that is left unaffected is that one, and then that one, and then that one, and then that one. And if we go back to our thing, if that's n equals 0 at the top, then the second one becomes n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and on and on. The term, well, the coefficient for our term is going to be n. 2, 2, 3, 3, 4, 4, 5. I didn't do 5, but it would be 5, and on and on. So, using Pascal's triangle, we know that n is going to be the coefficient for our thing, and using binomial theorem and kind of our own common sense, we know that the second term after x squared is going to be something xh, well, 2xh, since I put x squared, but, x to the n will be n x to the n minus 1 h. I apologize for my handwriting, it's getting a little cramped, but yeah, that's kind of like a halfway sort of proof for why the derivative of x to the n is n times x to the n minus 1. And using that earlier example that I didn't want to do, x to the 8th, the derivative of x to the 8th power, well, if n is equal to 8, then this is equal to 8 times x to the 8 minus 1. This would be 8 to the 8 times x to the 7th. And you can go as high as you want to. X to the, x to the 200, maybe, sure. X to the 200. That's just going to be the same thing. You have n, which is 200, times x to the n minus 1, or 200 minus 1, that being 200 times x to the 199. And I think that's pretty cool. What could have, if we used the limit definition, been a very, very difficult evaluation can be done in like 3 seconds once you know that the derivative of x to the n is n times x to the n minus 1. Okay, so that's a very important one, but we're going to go into some other ones. Another really important one is one that might not stick out as important immediately, but I promise you it is. It is the derivative of the natural logarithm of x, ln x. Now, for the derivative of ln x, you're going to have an understanding of what e is. Now, this might seem weird, but there are actually quite a few definitions of e that exist. Today, we're going to be concerned with the following. The limit as n approaches 0 of 1 plus n to the power of 1n equals e. There's a couple other definitions that there are. I mean, you may have seen the limit as n approaches infinity of 1 plus 1 over n to the power of n equals e. But for right now, it's just going to be the 1 on top. So remember that, and let's get into it. We're going to use our limit definition that we love oh so much. It will be the limit as h approaches 0 of f of x plus h minus f of x over h, which means that it will be the limit as h approaches 0 of ln x plus h minus ln x over h. Now, if you've done anything with natural logarithms, or even logarithms in general, you might actually know this rule. Ln a minus ln b is equal to ln a over ln b. And so, we're going to adapt that. We're going to say that this function right there is equal to the limit as h approaches 0 of ln x plus h wait, actually no, I'm good. It's the, let me erase that. It'll be ln x plus h over h all over h again. Now, we can rewrite this right here, since x plus h over h, if we were to split that into, two separate fractions, it'll be x over h plus 1, right? Because h over h is 1. So, let's keep that in the back of our mind. Oh, wait, no. I'm sorry. I've been losing it. No. What we're going to have, let me rewrite that, is ln x plus h over x. Yeah. And then x plus h over x is equal to x over x plus h over x. I'm sorry, that was weird on my part, but let's keep that in our minds. And then we have all over h. Now we're going to do what we did for, product rule, and factor out this 1 over h. We're going to have the limit as h approaches 0 of 1 over h times ln 1 plus h over x. Now, this might actually already be ringing bells to you over what we're going to do right now, but there is another natural logarithm property that you're going to have to know. It is a times ln b, a being just some random constant, not a function or anything. Well, it can be a function, but for now, we're just going to think of it as a constant. It'll be ln b to the power of a. That's a logarithm property that I'm hoping that is familiar to you. If it's not, I might do like some supplementary video on natural logarithms and logarithms. But yes, we are going to adapt our current formula, and we're going to put that 1 over h as the exponent. So we're going to have the limit as h approaches 0 of ln 1 plus h over x to the power of 1 over h. Now, if you remember what we had for our definition of e, at least in this context, you might be thinking that this looks familiar, and it does. We can actually alter this and introduce some arbitrary number u. We can say that u will be equal to h over x, and that h is equal to ux. Because, if we multiply that there, becomes h equals ux. Therefore, 1 over h is the same as 1 over ux, or 1 over u times 1 over x. So just think about that for a second. We have all of that, and we also have this new value u, which represents h over x, and we can perform quite a few uh, calculations with that. I'm just going to leave that one step, and I'm going to erase it. So now with this new u that we can alter, we're going to actually, I almost forgot one really important step. We need to alter our limit variable. Since we are using u instead of h in that area right here, we need to define as u, what u approaches as h approaches 0. So as h approaches 0, if um, if u is equal to h over x, as h approaches 0, then u will approach 0, because just based on direct substitution, even if as long as x is not equal to 0, then if you directly substitute h into that little function that we have right here, then u will be approaching 0 as well. So as h approaches 0, u approaches 0. That makes this way easier. We have the limit as u approaches 0 of ln 1 plus u to the power of 1 over ux, right? And let's actually split that 1 over ux into something else, ln 1 plus u, 1 to the u times 1 to the x. And now this takes into account a limit property and a logarithm property. You can bring this 1 to the x right there, remember, because a ln b equals ln b to the a. If a is this 1 over x, we can bring that 1 over to the 1 over x right there. But this also requires understanding of another limit property. We can actually bring it some other place. We can bring it all the way over here instead. As you may have done limits at some point, you might know that if there is a constant that can be factored out, 1 over x acting as kind of like a constant for our situation, you can bring it to the front of the limit. So it'll be, unaltered by like the calculation that we're about to engage in. So we brought our 1 over x to the very front. Then we have the limit as u approaches 0 of ln 1 plus u to the power of 1 over u. Now, based on our definition of e, it should already be pretty exciting, because if we bring ln out there, I know this seems somewhat odd, but actually, you know what? Sorry, I don't know what is wrong with me today, but we're not going to do that. What we are going to do is, using our definition of e, we can understand that the limit of u to the 0 of 1 plus u, 1 to u. Okay, I'm sorry again. No, I've been doing this for way too long. We can take the ln out. It is an operation, and a limit property allows for you to take specific operations that don't alter the limit itself, like the natural logarithm. It allows you to take it past the limits like boundaries. So using our definition of e, which is the limit as u approaches 0 of 1 plus u to the power of 1 over u equals e, this should already be somewhat exciting. We have 1 over x, and then the ln of the limit as u approaches 0 of 1 plus u, 1 to the u, which, as we defined there, is e. We have 1 over x times ln e. Now, the natural logarithm is simply a logarithm with base e. That being like the logarithm of something, some b with base a is equal to x. That's saying that a to the power of x is equal to b. Now, since we have our natural logarithm, which is a log with base e, and our thing right there is e, our input, we can make this 1, because e to the power of 1 is equal to e. So, drumroll please, the derivative of ln x is equal to 1 over x times 1, which is 1 over x. That's great. But you might be wondering, how can we find the derivative of something with an input other than x for ln x? Because, we have our ln x, that derivative is equal to 1 over x, but how is this more applicable to other functions like ln x cubed plus 3x, for example? We're going to use that one because it combines the two derivatives that you now know. You know the natural logarithm derivative and the derivative of x to the n. This one requires the chain rule. I think I mentioned it at some point, but the chain rule is, in my opinion, the most important rule because it allows you to do more complex derivatives. Because while understanding the derivative of just ln x is fine, we're going to need to know the derivative of what's inside. So let's do that. Let's break this ln x cubed plus 3x into a separate function. Not a separate, two separate functions. So I think you might know we have ln and we have some input. That means that the function of that input, which is going to be x because, this is a function of x, the function of that input will be ln x. That's saying that if f of x is whatever that is, then we're trying to find the natural logarithm of that thing. So knowing that f of x is equal to ln x, you might immediately deduce that we are also going to have g of x is equal to x cubed plus 3x. That is this function right there, and the input of any x will become x cubed plus 3x. So this function, ln x cubed plus 3x, is a function of functions. It is f of g of x based on what we've defined. So we're going to use the chain rule. We're going to have the derivative of that. Let me show that operation. The derivative of these functions, it will be f prime g of x, where the g of x is unchanged, times g prime x. Let me, well, I can't do that. There's just this little dot next to the f that's kind of bugging me. But we have f prime g of x times g prime x. So how are we going to do that? We have our input, which will be g of x, and if the derivative of ln x is equal to 1 over x, then if that input was x, then f prime g of x is just going to be 1 over x cubed plus 3x. It'll be 1 over g of x because, if ln x, I'm just going to rewrite it again. If ln x is equal to 1x, then ln g of x will be 1 over g of x. So, with that, let's put this together. We have 1 over g of x times g prime x, which is x cubed plus 3x. Now, let's evaluate this. I'm not sure if I should give myself some more room, but I might as well. Just remember we have 1 over g of x, we have g prime x, and f of x is equal to ln x, and g prime x is what we're going to find. So with our 1 over g of x, which I remind you was x cubed plus 3x, I'm going to actually put that down at the beginning. We will have x cubed plus 3x times g prime x, which means that we're trying to find the derivative of x cubed plus 3x. Now, I suppose on a smaller scale, this is also the sum rule, because we have, I guess you can consider this as a function and then this as a function. So to find the derivative of this, we will have to do the derivative of x cubed and then add that to the derivative of 3x. So I'll do my work off here. This, I suppose this also takes the constant times a function rule, but x cubed, the derivative of that, if n is equal to 3, then let me write down the rule once more. N x to the n minus 1, then if n is equal to 3, we will have 3 times x to the 3 minus 1, that being 3x squared. And then 3x is like 3, if we're trying to find 3x prime, that will be 3x prime. And 3 times x prime, this is a pretty easy one. 3 times 1 x to the 1 minus 1, because n is equal to 1 for that. So if 3 times 1 to the 1 times x to the 1 minus 1 is what we're doing, 1 minus 1 is 0, and anything to the power of 0, like x to the power of 0, is going to be 1. So let's write that down. We have 3 times 1 times 1, which is simply 3. So we have 3x squared and 3. That's the derivative of x cubed and 3x respectively. And using our sum rule, the derivative of 3 x cubed plus 3x will be 3x squared plus 3. Okay, so if we put all of that together, we have this equals that, right? So we have the derivative of ln x cubed plus 3x. That is equal to 3x squared plus 3 all over x cubed plus 3x. All of this is to show you that with the chain rule, and in conjunction with the other common derivatives that I've taught you so far, you can do quite a few derivatives, but you have to use all of these rules in conjunction with the common derivatives that I'm about to teach you. ln x in specifics is very important, both for differentiation and the inverse of differentiation, integration, which I will get to in a future video. But yeah, I'm hoping that you can see where the chain rule comes in to play for calculating more complex derivatives. And I'm going to do another very useful derivative, the derivative of e to the x. The derivative of e to the x. Now, to show you this definition, we're actually going to use chain rule once more. This is going to be a somewhat simplistic proof, but it is a useful one. So that we know that the derivative of ln x is equal to 1 over x. And we know that ln e is equal to 1. But ln e to the x, or the natural logarithm of some e to the power of something with base e, that's going to be x. If x was equal to 1, then log, the logarithm of e to base e would be 1. And then if x was 2, log base e of e squared is going to be 2. And essentially, ln, oh, whoops, ln e to the x is equal to x. So with those things in our head, instead of directly trying to find the derivative of ln of e to the x, we're going to do ln, we're going to set this up as a fact. We're going to say that ln e to the x is equal to x. And then we can say, with that, if we were to take the derivative of this and that, then the derivative of ln e to the x is equal to the derivative of x prime. So x prime, well, we just did this one, but for the sake of practice, x prime is equal to x to the 1 prime. You might want to do something like that. And if n equals 1, then we can do 1 times x to the 1 minus 1, and anything to the power of 0, because 1 minus 1 is 0, is going to be 1, so we have 1 times 1, which is, again, 1. That means that the derivative of ln e to the x is equal to 1. That's important. Now we're going to try and find the derivative using chain rule. We will have some random function. We will call it like, how would I write this? Okay, so I'm going to set up some function u equals e to the x. Instead of trying to find the derivative of that immediately, we're going to try and find the derivative of ln u, right? So the derivative of ln u is going to be the derivative of ln u, which is 1 over u, times u prime. We can think back to chain rule for that one, because we have u as some defined function e to the x, and we have this function ln u. So the input is that one, and I suppose if you wanted to, you could do like an f of x is equal to ln x, and then u of x is equal to e to the x, and then you could do f prime u of x times u prime x, and then you'd have that derivative of e to the x right there, and then 1 over u to that. But yes, essentially this 1 over u times u prime is just a natural extension of our chain rule, because, you know, the derivative of ln with some function x is going to be 1 over x, and if our function is u, then it'll be 1 over u times u prime, u being some function of x that's not x. Well, it could be x, but for our purposes, it's not going to be. It's going to be e to the x, right? So with that, like, rule set, pretty confusingly explained. I'm sorry for the just complete shift in our notation, but I thought that this might be a little bit easier to look at. We have 1 over u times u prime, and that's equal to 1 over e to the x. Well, let me write that back down. We have u is equal to e to the power of x times the derivative of e to the power of x, and we know that ln u, if u is equal to e to the x, we know that ln u prime is going to equal 1. All of that's going to equal 1. So I almost forgot the prime right there. That would have been a very boring proof of how 1 over e to the x times e to the x is equal to 1, but we have 1 over e to the x times e to the x prime is equal to 1. That means that if we multiply this e to the x to this side, then the derivative of e to the x is equal to e to the x again. Now, that might be even more of a somewhat boring proof than, not proof, but it might be more boring of a common derivative than the derivative of ln x being 1 over x, but I promise this one can also be useful. Let's try and find the derivative of e to the x squared. I'll keep it simple. So, e to the x squared, we have our function e to the x, that derivative, is equal to e to the x. Now, if we define e to the x as a function of f of x, then f of x is equal to e to the x, and then g of x is our input for this f of x. It'll be x squared, as outlined there, right? So, with that, we can do our beloved chain rule. It will be, f of g of x prime, that will be f prime g of x times g prime x. So with this e to the power of x squared, we will have f prime g of x times g prime x, which, as we defined, f prime is going to be just the same thing, e x squared. If the derivative of e to the x is e to the x again, then if the input was x squared right there, then the output will be x squared again. So, let me try and erase this. With that, we can now do g prime x. That will be x squared prime, or g of x is right there. Oh, forgot the squared. So with that, the derivative of x squared, that will be 2 times x to the 2 minus 1, or ex squared times 2x. 2 minus 1 is 1, and then x to the power of 1 is 1 as well. So we have 2x ex squared. That's a somewhat complicated answer for a derivative, but it does show you how the chain rule can be used in a variety of ways, and some applications of the chain rule for, finding the derivative of something with base e. Now, I could show you a derivative of some exponential function with a base other than e, but I might need to save that for another video. This is already getting far too long for my taste. So we're going to just go straight into sine, cosine, and tangent, the trigonometric derivatives. So we're going to start with sine, and we're going to use our limit definition again. We have sine x prime is equal to the limit as h approaches 0 of sine x plus h minus sine x all over h. Now, I could show you a secondary proof for what I'm about to do, but this is a trigonometric property, and it's a pretty important one. But sine a, some property sine a minus sine b is equal to 2 cosine a plus b over 2 times sine a minus b over 2. Well, I wish I could show you the proof for why that is. It's not really relevant to what I'm doing currently. I can show you a proof for that if you would like, but yes, that is a trigonometric property that we are going to be using for this one. We can say that if a is equal to, x plus h, and b is equal to x, we can write this instead as the limit as h approaches 0 of 2 cosine x plus h plus x all over 2, because it's a plus b, and then minus, I'm going to have to erase that part, right? Minus sine x plus h minus x all over 2. And then all of that's over h. Now to simplify this, what we're going to have to do is the limit as h approaches 0 is equal to the cosine. I'm going to actually cancel, well, quote unquote cancel. We have 2x. Well, I'll show you what I'm thinking. We have 2 over h, right? This 2 is in the numerator and this h is in the denominator. We can in fact, since I can't believe I forgot, that is supposed to be a multiplication sign. But yes, since every operation in here is division, we can kind of divide. Instead of having 2 and h in separate realms, we can keep an h over 2 in the denominator. And then we can factor out that h over 2 and put it somewhere else. So I will do just that. We'll have the limit as h approaches 0 of cosine x plus h over 2. That's because, x plus h plus x over 2 is equal to 2x over 2 plus h over 2 if we split them apart, so x plus h over 2. But with that, we can now split this again. X minus x is 0, so we have sine h over 2. Sine h over 2 all over, again, h over 2. Now, if you've done limits before, this might look like a very familiar limit, hopefully. Truly. I really hope that you've seen this limit before. But the limit as let me not use h for this one. The limit as x approaches 0 of sine x over x is equal to 1. Now, if we kind of, substitute an x for our h, if x is approaching 0, h over 2 will also be approaching 0 because it's a direct substitution for h over 2. So with that, we can now rewrite all of this as, just keep that in your head. We have the limit as h approaches 0 of cosine x plus h over 2, that's in parentheses, times the limit as h over 2 approaches 0 of sine h over 2 all over h over 2. And this is analogous to x for that same one that I showed you, the limit as x approaches 0 of sine x over x. So this comes out really nicely with just 1 on that right-hand side. And then using direct substitution, 0 for 0, we will have cosine x. That is the derivative of sine x. And, regardless of what's within that function, let me write that down. Sine x, the derivative of that is equal to cosine x. But if sine was some function u, like we used in that last one, sine x was some function, that was the worst u I think I've ever seen, sine u, then the derivative of sine u, if u is some function of x, will be sine u, or, well, it'll be cosine u times u prime, using our chain rule. So now we're going to follow that up with its natural brother, cosine x. We're going to again use our definition of a derivative. That will be the limit as h approaches 0 of cosine x plus h minus cosine x all over h. And then, again, I'm hoping that you guys have seen this one. This is another trigonometric property. Cosine A minus cosine B is equal to negative 2 sine. I don't know what's happening. It'll be negative 2 sine A plus B over 2 times sine A minus B over 2. I'm really hoping that you guys have at least seen something similar to this. If not, you can comment down below. I might, depending on how I'm feeling, do some type of basic trigonometry video, and I will tackle those properties. But we will plug in if A is equal to x plus h and B is equal to x. We will plug those in, and we will have negative 2 sine x plus h plus x over 2. Sorry for the slant. And we will have sine, forgot the h approaching 0. We'll have sine x plus h minus x over 2. All over h. Now, we will do the same thing that we did for our sine derivative. Because you guys have already seen it, I don't think it's necessary for me to spend too much time on that step, that interim step. But essentially, we're going to take our negative 2 and our h, and we will bring it to this side. It will be, actually, you know what? We're going to keep that negative on the left, and that will help in our final one. But we will take this 2 and this h, and instead of having 2 over h in the numerator, quote unquote, we will have it in the denominator as h over 2. So we'll have negative sine x plus h over 2 times sine h over 2 all over h over 2. So, take a second, look at that. Maybe write that down if you want. I'm going to erase all of this. And then, we'll put it together. We will have the limit as h approaches 0 of negative sine x plus h over 2 times the limit as h over 2 approaches 0. Because, if h approaches 0, then h over 2 approaches 0. Like we had in our last proof. So we will have the limit as h over 2 approaches 0 of sine h over 2 over h over 2, which again is analogous to the limit as x approaches 0 of sine x over x, which equals 1. We have h over 2, h over 2, h over 2, x, x, x. So this all, again, comes out pretty nicely to just 1 on that right-hand side. So we'll have times 1, and then the limit as h approaches 0 of negative sine x plus h over 2. Using direct substitution, we have 0, we have h. X plus 0 over 2 is x plus 0, which again is x. So we have negative sine x. Alright, negative sine x. I'm going to write that down once more, and I will again show you what it looks like using the chain rule. We will have sine x, no, not sine x, we're doing cosine x. Cosine x, and that derivative is going to be negative sine x. Fantastic. And if we were to define u as some function of x, we'll have the derivative of cosine u being negative sine u times u prime, u again being some function of x. Now, last but not least, we are going to do tangent of x. Tan x, we're going to do that derivative. This one doesn't require any special knowledge of trig properties. Well, maybe kind of a little, but it will have more to do with our derivative friends. So we have sine x over cosine x. As you may or may not know, sine x is equal to tangent x is equal to sine x over cosine x. If we look at our right-hand triangle like that, if sine x is the opposite over adjacent, opposite over hypotenuse, and cosine x is the adjacent over the hypotenuse, and tangent is the opposite over adjacent, then O over H over A over H is equal to O over A. That's, just a basic way to explain why tangent x is equal to sine x over cosine x. And with that, we find the derivative using quotient rule. Yeah. So, if you remember, we have f of x is equal to sine x, and then we have g of x is equal to cosine x. And then using quotient rule, we can do f prime x on the top, which is sine x prime, times cosine x, which is our g of x, minus sine x, which is again our f of x, times g prime x, or cosine x prime, all over g of x, or cosine x squared. Okay, so with that, we can plug in some stuff that we know. We have sine x, that derivative is cosine x. We have cosine x squared minus sine over x times sine over x, well, times negative sine over x, sine x times negative sine x, all over cosine x. Okay, times cosine, why is that happening? Times cosine x squared. And now with that, we can cancel out this negative and a negative. It'll be a positive. We'll have sine squared x, which is, sine x times sine x is sine x squared, or, sine squared x. We have sine squared x, and then on this left, we have cosine x times cosine x, which is cosine squared x. We have positive sine squared x and positive, whoops, and positive cosine squared x, which I feel like this might actually be a little bit more easy to know. This is 1. Not over 1, but it's just equal to 1. So we have our derivative of tangent x be 1 over cosine square x. And you might actually be familiar with the concept of 1 over cosine x being secant x. 1 over sine x will be cosecant x, and then, 1 over tangent x will be cotangent x. But yes, if 1 over cosine x is equal to secant x, then the derivative of tangent x will be secant squared x. So, again, we'll write that down. That will be 1 over, not 1 over, we will have just secant squared x. And we have that same chain rule application will be secant squared u times u prime. But that was a lot. I'm going to try and write down everything that we've done so far. The derivative of x to the n is equal to n times x to the n minus 1. The derivative of ln x is equal to 1 over x. The derivative of e to the x is equal to e to the x. The derivative of sine x is equal to cosine x. The derivative of cosine x is equal to negative sine x. And then the derivative of tangent x is equal to secant squared x. Now, these are all useful, but they have limited uses if you only care about x. If you define u as a function of x, and you plug in u for these ones, well, not for that one, but for this one, you can have ln, u is equal to 1 over u times u prime, and then e to the u will be u. Quotient rule, you can kind of do most of the derivatives that you're going to have to do, but there are obviously more complex ones out there. There are the inverse trig identities. There are, exponential functions with a base other than e, which I will teach, I promise, in maybe a supplemental video to this one, a part 2. I really don't know. But yes, those are all really important, and along with chain rule, they will form the bulk of your differentiation. Now, let's talk about the last topic. If you manage to watch all God knows how many minutes of this, I commend you. I don't have the strength to watch me back all this time. But if you did, you get a cookie. We're going to tackle one last topic. I was thinking perhaps I could tackle differential equations, but after checking how long I've been recording, like a little while ago, I don't think that's going to be possible. But we will do, I mean, it's possible, but I really don't want to. We're going to be doing implicit differentiation. This is a very important topic for both single-variate calculus, but in multivariable calculus is where implicit differentiation kind of shines. But right now, we're going to do, I wouldn't say it's a differential equation, but it's a way to show you how implicit differentiation works. I will have this function, x cubed plus 3xy plus 7y squared equals 3. Sure. And we are trying to find dy dx. I know I haven't been using dx notation very well, but yes, if you can remember, if y is equal to, f of x, then f prime x would just be y prime or dy dx, or the change in y with respect to x. Now, you might be wondering, how can we take the derivative of this? We could. We could explicitly define y as a function of x. We can define it like y equals f of x, and we can isolate the y through some magic math powers, and everything will be fine and dandy. But that calculation would get very ugly very quickly. I know this one isn't too bad, but if we were to try and, isolate the y, we would have to factor out some y's here, since these are different powers that would actually make it even more difficult. And trying to find some perfect y equals f of x function just isn't going to work, not for our purposes. So we're going to keep y, and we are going to implicitly define it as a function of x. Implicit means that we acknowledge y is technically, yes, it is a function of x, so we are able to do a derivative with respect to x to our y to get some d over dx y. But we also acknowledge that this isn't explicitly defined as a function of x. We didn't find any f of x for this one. So this is going to use chain rule. We are going to isolate our y's on one hand. I prefer having it on the left, but, a couple of people like to have it on the right. And we will bring this x cubed to the right hand side. It will be 3 minus x cubed. Now, if we're trying to find dy dx, what we're going to have to do is use chain rule. So I'm going to actually rewrite chain rule in in our dx notation that we're trying right now. If we are saying that the derivative of dy dx is some function u, we can say that u is a function of x, and we can find the derivative du of dx times dy du. That's a different way of writing f prime g of x times g prime x. And this y and this u are interchangeable. In fact, more often than not, you'll have your du's on the left-hand side. Du over dx is equal to dy over dx times du times over dy. But essentially, we're saying that the derivative of some function that isn't explicitly defined as a function of x is that function, but times a arbitrary dy dx. So, yeah, what we're going to do right now is exactly that. We have this 3xy and this 7y squared, and we don't explicitly know that this is a function of x, but we can treat it like one. We can implicitly define it as a function of x and then differentiate it. So that's what we're going to do. We're going to have 3xy primed. We are going to use product rule. We're going to say that 3xy primed is the same as, if y is some function of x, that means that 3x is some function of x. So these will be multiplied, and then to do that, it will be y primed 3x times dy dx and a 3x prime times just y, because we're not taking the derivative, and that would not be necessary. So I suppose a way of writing this would be the d of dx of some function y is equal to that d dy times dy dx. Yeah, so this d dy will be the derivative of something with respect to y. Oh, that's not the correct example. So essentially, if we have a function y and we're trying to find the derivative of it without explicitly defining it as a function of x, that means that we will take the derivative of it normally as a function y, but then we will multiply it by some dy dx that we don't currently know. So if y is not officially defined as a function of x, well, then we are going to have 3xy. We're going to do the prime of that plus 3x y prime dy dx plus 7y squared if we're trying to find d of dx of 7y squared. We're going to have the d dy, or the derivative with respect to y, of 7y squared times d y dx, which is what we're trying to find. Remember, this is the goal. We're trying to find the derivative of y for that function at the top. So let's get that. Let me erase some of the stuff. We have 7y squared prime times dy dx minus the derivative of x cubed, or 3 minus x cubed, I suppose, but as we know from one of our rules, the derivative of a constant is going to be 0. But we have 3x prime, which is 3. If n is equal to 1, we will have, 3 times 1 x1 minus 1 times y plus 3x. And this is the important part. We're going to treat y normally. We are doing a d dy for that y right there. That's what this y prime means. But we just have a dy dx that we are also trying to find. That will be separate. It's not something that we're going to calculate right now. So you'll have 3x times 1y, 1 minus 1, times